build an Ethereum consensus client in Rust called Lighthouse. So this is an open source project if you guys ever want to have a look at any of the stuff that we're doing. It's called Lighthouse, so forewarned, there's going to be a few pictures of lighthouses in these in this talk. I get my little clicker. So yeah, we do a bunch of security stuff as well, so I figured a talk generally about security and Rust would be useful. Fuzzing in particular is something that's pretty straightforward that you can do, and it can pretty much improve the security of your project. So it's pretty easy to do, it's pretty handy. The talk's very lightning, it's a very intimate, a very basic talk, so hopefully it's useful. I did also steal some of these slides from my colleague Mehdi as well, so he might be able to answer some of these things shamelessly, I might add. So let me start with fuzzing. Fuzzing 101, what is fuzzing? So fuzzing is a process or a tool that we can use that essentially you get a bunch of random inputs, a lot of random data, and you can inject it into a particular function and see how that function behaves. Most of the time, hopefully, if you've programmed the function correctly, the function is going to continue working normally. But you'd be surprised that if you input someone's expecting the number 10 and you put in 100 billion and then the whole program explodes, this is the kind of stuff that fuzzing can kind of pick up. So fuzzing essentially is just finding a particular function or some element of your code base that you want to test. You want to make sure that it's robust, and then just getting a fuzzer, which is something that just machine gun shoots a bunch of inputs to it and hopefully seeing whether it still stands up. It's a little bit smarter than that because fuzzes, if you have the source code, it allows you to do coverage guided fuzzing. So what that means is the fuzzers get some arbitrary piece of data and then they mutate that data a little bit at a time, and they mutate it in such a way that they're trying to elude or get as much code coverage of all the different code paths within that function as it can. So if it finds one input that gets to another, it gets to a new area of the function that it hasn't seen before, it kind of saves that and then mutates that to try and go further on. So this is essentially the concept of fuzzing. We want to try and go through all the different kind of code paths of a particular function and make sure it doesn't explode, make sure it does what we expect. So in Rust, that kind of looks like if we see a panic from something that we put in, then that's usually a bug or there's something wrong. Makes sense, hopefully. Pretty straightforward. Cool. Okay, so fuzzing in Rust. So this is pretty easy. It's not too hard to do. There's a Rust Fuzz book. That's the URL to it. And I also shamelessly stole like 2 slides from them just to show you how kind of easy it is to do fuzzing in Rust. So in this book, they show you an example. And this is an example. You have a fuzz target macro. This is all you have to kind of input. So you create things called targets. So these are essentially the functions or the areas of code that you want to send random data to. And once you have set up a specific target, you just run cargo fuzz after installing like a particular fuzzer, and it will go and machine gun a bunch of random data into your function and tell you if there's any panics, essentially. So the way that you do it, you have this fuzz target macro. The input value is some arbitrary data, right? And this is what the fuzzer is going to inject for you, and it does it in a smart way. So it mutates it's called a corpus, and it mutates the original data to try and find all the code paths. So in this particular example, it gets the random data, it converts it into a string, and if it's a legitimate string or if it does an error, then it tries to pass it as a URL. So it's testing decoding the URL decoding in this example. And according to the book, if you run this for a little bit, this actually finds a bug in the URL parser that a specific string which starts with HTTP gives you an index out of bounds. So it shows just this simple 3 lines of code found a bug in this parser where they didn't account for a particular string that you could pass in there, and it explodes. So this kind of stuff is particularly useful if you have functions that are either getting user input or you're getting information from the disk or from network or from some unverified source, and then you've got let's say a compression algorithm, or you're decoding something and you run it through a decoder. You need to make sure that some random person isn't carefully crafting a particular input that explodes your program. And I'll show you an example of that a little bit later on. Okay, so getting random data and then dumping it into a function, that's not always that useful, especially if your function doesn't just take random data, right? Usually you're going to have some particular type. You'll have like an enum, a struct, or a bunch of different fields that needs to go into some complex function. So we have a thing called structured fuzzing, which is essentially allows you to define a struct or a type, and if you just have to implement this arbitrary trait. It's a trait in Rust. You can derive it as well if the types also implement arbitrary. And what the arbitrary trait allows you to do is it can generate arbitrary versions of whatever struct you want. So you can have some. So essentially, you get input random data, and the input random data will spit out a random version of this struct that implements the arbitrary trait. So the example of this is if you have some struct called RGB, you can implement arbitrary on it. Then you set the fuzz target like we did before. So instead of it actually inputting random input data, you can now input this type that you might need for your function. That type the fuzzer will mutate it gradually through the random data, and it'll give you this like new versions of this particular type. So in this particular fuzzing target, we're converting color to HSL and then converting it back and then making sure that they're equal. That's what the fuzzing is going to do. And then you run this thing for arbitrary number of hours, and it's going to try and find all the different code paths that are in the two functions that convert to HSL and convert back, and see if there's any kinds of versions of this that differ. And if it panics, then you found something bugged, so something unexpected. And you can do this. So even though these are kind of simple examples, you can do these on very large, complicated functions inside your code, and the code paths could be very many, very deep, and it tries to go through all these things, and you can find bugs in a bunch of your dependencies. So structured fuzzing. So that's generally fuzzing in a nutshell, how to do it in Rust. If you have particular projects, it's very easy to do. As you can see, you just build some of these targets and then run, and it shakes out, it's very effective at shaking out bugs that you might not otherwise see. So I kind of highly recommend if you have something sensitive. Okay, so I want to talk just briefly in the last 2 minutes that I have about how we use this in our day-to-day. So in Ethereum, we have the concept of these nodes. They're called beacon nodes. They are essentially little pieces of software or little computers that are running around. They form a distributed peer-to-peer network. They send messages amongst each other across this distributed network. They all have their own local view based on the messages that they gather of a blockchain. And there's 5 different versions of these clients. One is ours. It's written in Rust. It's called Lighthouse. There's Lodestar. That's written in JavaScript. Nimbus, written in Nim. Prism is written in Go, and Teku is written in Java. We launched the network in 2020, but the point is we now have on this distributed network 5 different clients across 5 different codes or implementations, and also languages. So the interesting thing we can do then is called differential fuzzing. So instead of having a random piece of data and putting it into an individual function and seeing if the thing explodes, we can get a random piece of data and we can put it into each individual implementation of the client that's supposed to do the same job, essentially. So we have a specification. If we get a block or some specific piece of data, they have to process it in a specific way. If they process it differently to any of the other clients, we can get a very critical error called a chain split. So in blockchain, if one implementation decides, oh, I've got this transaction, I get this piece of information, and therefore the result is X, and everyone else thinks the result is Y, they fork from the chain, and this is a very critical consensus problem. They all go off in their own land, and they lose money, and it's a really bad thing. So all the implementations have to do the same thing all the time, and if they don't, it's very, very, very bad. So we can do this process called differential fuzzing, which is where we get some random data, we give it to all the clients. If any one of them is different, then that's bad, and that's naughty, and that's a bug. So differential fuzzing is something you can do if you have something of this form. So we have a open source project, community project called Beacon Fuzz, mainly Mehdi's child, and this thing was designed. I think the general idea was, let's give this to the community, and everyone can run these fuzzers. They can run it in Docker, they can run it, they can use the processing power to just dig out, and then it's like a community effort to find bugs in Ethereum. And it essentially will go off and generate miscellaneous consensus objects, so structured fuzzing, some complicated things, and give it to all the clients, and if any one of them are different, it logs a big error and says, you found a bug. What could go wrong, right? So I think now there is a public version of this, but it's now private because this thing was quite effective at finding severely critical bugs in Ethereum and the blockchain. So I think we decided it's not so good to be public, considering the number of bugs that this thing found. And if you find one of these critical bugs, you can essentially send some of this data to the network and just boom, it's all exploded. So we're like, we're not going to make this public anymore. So it's still public, you can still use it, but it's kind of outdated. Okay, yeah, so this is the Beacon Fuzz project. That's where it's located. It's in our repository called Beacon Fuzz. If you want to have a play around with some of this differential fuzzing, and if you find a bug, tell us, don't exploit it. But hopefully this is old enough that you're not going to find anything. We've run a bunch of fuzzes on these. Yeah, don't exploit it. Tell us, be good. So the Beacon Fuzz architecture, it's probably worth just briefly going over it in case you're interested. So with structured fuzzing, we need to start, it's usually good, instead of just sending random data at some really complicated function, you want to give it a head start. You want to give it something that's valid so it can pass a bunch of checks, initial checksums, and make sure that it's encoded in the right format before you can start hitting some of the meaty logic. So you can I guess, dump some of this stuff into some initial fuzzes. They can use that and then mutate from there to try and improve the code paths, or to elucidate the code paths, enumerate. So let me just quickly, I'll quickly go over this because I'm running out of time. Eth2 Fuzz, this is what's inside the project. This thing can target each individual client independently. It does structured fuzzing. It can find a bunch of different kinds of bugs. So this is where we implement the arbitrary trait in Rust on individual specific types, and then do all the clients independently. So it finds things like out-of-bound memory accesses, panics, integer overflows. Some of these stuff is not applicable to Rust, but the first three, I think, are very important. We do have memory exhaustion as well. I'm going to just skip this one. It's not really important for you guys, but it's kind of cool. And the Beacon Fuzz 2 project, this is the differential fuzzing. So we can get some of the outputs from the Eth2 Fuzz that they found interesting in particular code paths, mutate those, and then this thing will this thing knows about the similar functions across all the different languages. It uses FFI. I always think of fast Fourier transforms, but that is foreign function interfaces that connects to each of them on different languages, and it sends the same mutated data to each of those things, and then looks for differences or panics. Yeah, so this is the differential fuzzing engine, and it allows you to find some more meaty kind of bugs, and it's surprisingly effective. There's a lot of code in each of these clients, and everyone's doing it differently, and this shakes out like a bunch of issues that could otherwise happen. So let me give you some examples of things that we found. I'm only going to give you very quick ones. One is in our decoder we use Snappy as a compression algorithm, and inside Snappy, so this is just a dependency. So there's no code that we wrote, and essentially we have some arbitrary data. We compress it, send it across the network, comes back. We decode it, and boom. The fuzzer found that with some weird initial state, you can send it to Snappy, and in the decoding process, you have a weird length that they weren't expecting. If you can see, yeah, they don't account for at a particular point that the length being a particular size, and they do an integer underflow, which panics in debug mode, but it causes it gives you some weird error and is unexpected in release. So this is a compression library. So a lot of compression libraries and decoding libraries, you can find a bunch of kind of weird bugs. So naughty, snappy. So that's something that we found. But I'm not just going to point fingers. This is code that I wrote, and it also found something in there which is pretty nasty. This function, which has got a bunch of things, the reason I'm showing you the bunch of code is this is from a library called Discovery v5. It's a protocol that we use for all these nodes to find each other in a distributed network. But the code path here is, again, it's someone sends you arbitrary data on the network, and we need to decode it. But the arbitrary data is encrypted. It's got a bunch of different magic packets at the thing. There's a whole heap of things. So there's one condition. It's it's got to be encrypted with your particular address, and then it's got to have this magic packet, this magic packet. There's a bunch of steps that you'd have to do. And then at line 471, we take a particular index or slice of this data, which after it's passed all of these checks, and then move it to somewhere else. I missed this IV length size when I wrote this. And this causes an index out of bounds, and it causes it to panic. So if somebody can craft a malicious packet, so with all of the right things at the start, but then this little naughty arbitrary amount of binary, the node explodes, which means that on the network, you can just get one node and just send it to every person that you know, and they all just explode. They all panic. So naughty. And that's also, this is code that I wrote, so this is my bad. We fixed that, so hopefully that doesn't happen anymore, but you can see the kind of sensitivity that these things find. Yeah, I spent a bit too much of my time, so any questions? Ours, of course. Oh yeah, sorry, I should repeat the question. What is the most reliable implementation? And it's got to be Lighthouse because it's secure, yeah.
Yeah, I haven't used this macro, but there's this thing called the no panic macro, and it like checks for like parts of the code where it will panic. Say if you use unwrap or like use unchecked indexing, it will pick up a compile error. Like,
Okay.
what's the question?
Yeah, I'll repeat the question. It's not a question, it's just a statement.
Like have you looked into using it? Like,
Okay. Yeah, so the question is there's a no panic macro that goes through your code, and if there's areas of your code that can potentially panic, it lets you know, or maybe it doesn't let you compile. It's a compile error. I haven't used it. I don't know about it. There are parts in the code that I actually want to panic. We don't do it often, but there are other things. I imagine that would be handy in some very critical areas. I haven't used it. I probably should. There are other things that we came across, such as things where there's some encoding schemes where the first byte represents the size that you're supposed to download, so then you have to pre-allocate some buffer with the size. And if someone puts 100 billion in there, then you exhaust all your memory and things explode, stuff like that.
is there any other questions?
Yep.
This is a quick one. What's the difference between fuzzing and property-based testing?
That's my question.
Yeah, okay. That's a good question. I don't actually particularly know the... Oh yeah, sorry. What's the difference between property-based testing and fuzzing? Right, that's the question? Yeah. So I don't have a good answer to you. Maybe Mehdi does. He can probably jump in. Fuzzing's not really my...
Property-based testing, you perhaps refer to that quick.
Yeah.
Yeah, cool. So you find a lot of fuzzers that are actually built using quick. So it's hard to...
Can you go from speak?
Yeah, microphone.
I don't really have much to add, but so the question was, what's the difference between property-based testing and fuzzing? Quick is a framework, popular framework for property-based testing, and I was saying that a bunch of fuzzing engines are actually based off Quick. So I think it's very hard to draw a line between the two testing methodologies.
Isn't the property-based testing just so you can click in the CI and complete it? And the fuzzing is like you search for the little pinhole in a big nuclear star.
Yeah. Yeah. You also need a massive, like 10 massive machines with 100 cores. We have. There's 4 different boxes that have 500 cores and like a.
512 cores, and I think we're up to...
But you must be like leveraging the whole internet, have like a miner, fuzzing miner.
Yeah, it's a little bit like, I think someone was talking about the Barcelona supercomputer at one point. They're like, we have some time on this thing. But that was the idea with the community fuzzing. It's like, everyone can use their own computer to do this thing, but yeah, exactly.
There's some request.
Very quick one. So actually, I think this alludes to when you use it in your development cycle, right? So property testing, obviously, during testing time. This is not during testing time.
That's right, yeah. Yeah, that's right.
Can you just elaborate on that a little bit?
Yeah, so we have this whole project which is an ongoing thing that which have these fuzzers running fairly regularly, especially for when new code gets updated across all of the clients. So each of the individual clients, we're doing regular upgrades, especially sensitive ones to the core consensus thing. We then build new fuzzers and we kind of run this somewhat regularly. Yeah, quick.
How do you manage your state? How do you test out against your state from testing? How do you state the state?
Yeah, if you like.
You can go.
Yeah. The question is, how do we get the actual application state in fuzzing?
Yeah, I'll jump on this one because it's a massive challenge that we find where every time there's statefulness associated with an application, it's really complicated to get meaningful fuzzing done. We sometimes request developers to expose certain interfaces to allow us to hit the core critical business logic.
Try record replay.
We have for network traffic. The question was whether we've tried record and replay, and we've actually done that for certain network targets. But it is very tricky, and it's even more difficult when you have differential fuzzing and you're trying to do this in 5, 6, 7 different languages.
One more question.
Yeah. Just to finish off your question as well, Chris, we do it for specifically, if we change any parts of the decoding logic, stuff that comes from the network, stuff that's unverified or unvalidated, particularly be like, okay, we need to fuzz this thing.
Cool.
Yeah.
Awesome. Thank you for.
Cool. Thanks. Thanks, everyone.